Welcome to today's ARC Center of Excellence for Enabling Eco-Efficient Beneficiation of Minerals signature lecture series. I'd like to start by acknowledging the traditional custodians of country throughout Australia and their connection to land, sea, and community. And we pay our respects to their elders, past, present, and emerging, and extend that respect to all Aboriginal and Torres Strait Islanders people today. We're fortunate to have Tim Hunter here from Leeds. He's actually in Melbourne visiting some family and was here, and we've had a good morning of discussing with the students and researchers the work they're doing. And so Tim is going to present his work on advanced measurement and process intensification techniques for nuclear effluent and sludge treatment. Interesting links to the beneficiation of mineral waste. So with that, I'll let Tim have a chat.
Great. Hi all, thanks for joining online, and thanks for those of you here joining in person. Apologies for the wordy title, I won't say that again. But essentially why I'm here today is talking to you about some of the long-standing work we're doing with the nuclear industry in the UK on sort of sludge treatment and liquid effluent treatment, and how we're using process intensification to help develop new processes for the nuclear industry, and what sort of knowledge, transfer and interesting links there are to waste treatment in the minerals industry and minerals processing. Oh, didn't do very much, did it? What else will I press to move forward? Okay, just what do you? There's no roller on that thing. So I'm using George's Mac laptops, not something I can really get my head around, to be honest. Anyway, what I'm going to talk about is give you a little bit of a background into the UK nuclear legacy and the community that we work with in the UK, and also give a big background on process intensification, which may or may not be a terminology you're familiar with, but certainly you will be familiar with some of the processes that are under the banner of process intensification, and also talk about online measurement technique and how they're linked. And then I've got an example of some of our long-standing work using acoustics for online characterization of particulate sludges and suspensions, and then a couple of examples of us using sort of process intensification principles to help develop new effluent treatment and separation processes. And oh dear, work. There you go. I've got this wheel of fortune of process intensification that I'll go back into in a few slides, excitingly on the screen there. Just acknowledgements to the number of researchers that have contributed to this talk. I won't name them all, but there's, this is work that's been developed through a number of years with the nuclear industry and funded by a number of sources as well. Primarily, we work with Sellafield, which is the nuclear site license operator for the reprocessing and legacy treatment operations. And we get funding directly from industry and also for government sources such as UKRI and Horizon money from the EU. Just a bit of background on myself. I actually did my PhD in Newcastle, Australia, where I'm from, and my PhD was focused on sort of nanoparticle interactions with foam and using nanoparticles to stabilize foams and frothers. From that, I sort of a little bit of a sideways glance into flotation, although I was more focused on sort of fundamental dynamics of foam stabilization. And so essentially applied colloid science, and I took that knowledge to the UK. I've been in Leeds for about 15 years now, essentially applying the same sort of colloid science, but to nuclear waste processing problems. And hopefully maybe we can exchange that knowledge back out to some of you working more in the minerals processing area. And I do work outside of the nuclear industry as well. We do work with other minerals operators, and especially in the paints, we do a lot of work on sort of paint processing and pigment manufacture as well, and other mineral companies. But certainly in the UK, nuclear is quite a dominating influence. We have a lot of nuclear operational sites, but certainly our nuclear legacy is one of the largest in the world that we have to deal with imminently. And so that takes a lot of our group's focus. But there is a lot of application areas for applied colloid science that we look to focus our knowledge and expertise on. So a bit of background on the nuclear industry in the UK and on Sellafield, which is essentially one of the largest operational nuclear sites in Europe, and certainly the largest nuclear hazard site in Europe. It was the site for the first commercial reactors in the world, which were opened by Queen Elizabeth in the 1950s, but also primarily is where fuel was reprocessed. By that we mean extracting the uranium plutonium for nuclear weapons. Fuel has also been processed for domestic purposes, nominally to recycle uranium plutonium, although that recycling operation has never occurred in the UK. We just store all the separated plutonium and uranium. But initially, the desire was to produce plutonium for nuclear weapons, and this is where it all happened. And there's 3 or 4 generations of reprocessing plants on site, 3 or 4 generations of nuclear reactors as well. There's no active nuclear reactors anymore, but there is, cleanup activities resulting from these many decades of nuclear activities. So eventually, Sellafield will go into a period of care and maintenance, but at the moment, the focus is on active decommissioning and waste transfer. And it's a very congested site, and there's many thousands of buildings and many hundreds of nuclear radioactive facilities, encompassing many activities, not just in terms of power generation, but as I said, storing, transferring of waste and reprocessing to extract, the valuable products from a nuclear reactor, not just for electricity. And it is also the site of the first nuclear disaster, the Windscale fire, which you probably have never heard of, from 1957. It was, not many people did hear it because the government hushed it up at the time. And it wasn't a massive release because of filters that were put on the big stacks. You can see one of the stacks being built in the black and white photo. And there was a lot of debate at the time about the need for particulate filters. But luckily somebody went out and installed them, and therefore there wasn't a big release of radiation, but it was a fire in one of the reactors that they still haven't managed to fully decommission the reactor. So there's a lot of activity that needs to be dealing with from a risk management perspective. In particular, we do a lot of work with them on their open air ponds. Now, if you were designing a nuclear waste plant now, or a nuclear reactor now, you'd never design an open air pond. Obviously, it leads to massive exposure risk. It also leads to massive wear. Sellafield is built in the Cumbrian coast in North England. It's on the coast, so lots of salt air. It's cold. There's a lot of corrosion and erosion of the concrete that has occurred. These were built with an estimated lifetime of sort of 30 to 40 years, and they were built in the 60s and 50s, and so we're coming up to 60, 70 years post them being built, and 20 to 30 years post their expected life expectancy. There is a lot of corroded, contaminated sludge presently within the ponds that needs to be transferred to safe long-term storage until we can eventually decommission the ponds themselves. And there are a number of sites, a number of other silos, etc., where active waste transfers are taking place. But the cleanup bill is big, estimated probably around £100 billion over the lifetime up to 2100. These are very long timescale cleanups as well. The Sellafield site takes about £2 billion of taxpayer money per annum, of which a lot of the operational costs over the next 20 to 30 years will be directly on waste processing. So anything that we can do to work with industry to reduce that bill, and increase safety and reduce risk on site is warranted in its own right. But these are sites that have explicit need to be decommissioned over relatively short timescales in terms of nuclear timescales, which are very long. So some of what I'll talk about is directly on these pond transfers. And the rest of it is really about cleaning the effluent. So the pond goes through a series of ion exchange units currently, and some of what I'll talk about at the end is on new designs for modular ion exchange units. So about process intensification, this is a term that sort of came out of the high value minerals and pharmaceuticals industry, more purposely in Europe, sort of 20, 25 years ago. essentially there's a number of definitions, but one I've got here: any chemical engineering development that leads to a substantially smaller, cleaner, safer, or more energy efficient can be called process intensification. But the key is using new types of process units or reactors to lead to step changes in efficiency and step changes in sort of energy reduction and space reduction. And so the sort of there are a number of tenants, but essentially we talk about units that are developed to be scaled out rather than scaled up, essentially. So those units have high dynamic efficiency, that have reduced energy and waste because of the high dynamic efficiency, and therefore reduced footprint or modular flexibility as well. There's many types of designs that people have looked at. It's primarily from sort of mass transfer perspective, types of reactors that are used, say for organic production of pharmaceuticals or catalyzed reactions. But generally, it's about small, efficient units that we can use modern manufacturing methods, so that the old tenets of scale up no longer apply. If you can make things cheap enough, you can scale out rather than scale up. And a lot of process intensification on the mass transfer side is sort of focused on these sorts of smaller, high dynamic efficiency units. And for the nuclear industry, they're very concerned about space. The picture before of Sellafield, it's a very congested site. It's a set of thousands of legacy buildings. There's not a lot of room to build new treatment plants for liquid effluents or solids waste treatment. So anything that can reduce the footprint in terms of a radioactive plant is accepted anywhere, but certainly on legacy sites where there's a lot of pressure on space, this is something they're particularly looking towards. And it also links, highly on our work on online measurements, because you often can't extract the maximum efficiency out of these sorts of units without feedback and control. So use of online measurements for active feedback and control is another important part of process intensification. Again, using modern technologies of sensors and modern artificial intelligence methods for control, for example, to maximize the unit efficiency that you can obtain. So just to give you a sort of a general example, you've got a traditional scaled up stir tank reactor, or that you'd scale up and make it bigger because you get more pound for the surface area, but they're not efficient in terms of residence time distributions. You have very chaotic mixing, very high shear at the impeller blade and very low shear outside of that. And so, a lot of people, not ourselves, but a lot of people have sort of focused on, well, if you compare that to, say, a plug flow reactor, but with microchannels. So you have very small diffusion distances. So you have fast, reactions. And because of the slow diffusion, you have sort of reaction limited kinetics rather than mixing limited. And because they're plug flow, you have very reproducible mixing regimes throughout the whole of the channel. So you have small residence times distributions, and it's getting towards the point where these may be applied. Obviously, you may need hundreds or thousands of individual units. Manufacture of these types of units is cheap now because of modern etching techniques, for example. There is still an element of issues of control. If you have to have a manifold and pumping systems for thousands of microchannels, the picture there shows a few stacked together, but let's be honest, that's still not generating industrial flow rates there. So that this is sort of an extreme example in a way, and what we tend to look at is larger sort of tubular reactors that are more scalable to industrial needs, with lower levels of development on the control side of things, which is certainly one area that is holding up sort of applications of microchannels and other related technologies in industrial at the moment. In terms of nuclear and current applications of process intensification, one is a complete extreme example on the other side to using microchannels as a reactor. It's the use of small modular reactors. So this is increased attention, certainly in the UK. They put a lot of money into development of small modular reactors, mostly focused on Rolls-Royce, who are trying to use essentially their submarine type reactors for electricity purposes. There's companies in the UK, US, such as NuScale, And the reactors themselves, vary in terms of their sort of energy output. But it's a sort of concept that is similar to process intensification. They're designed at the end of the day to be something that can be manufactured off-site, so scaled out rather than scaled up. And because they're modular, they have the flexibility of being able to move into areas where they're needed, such as industrial areas, for example, rather than having an enormous central reactor, and then you have a lot of associated losses with transmission, etc. as well. So that's on completely the other side in terms of scale, but still, the concepts of process intensification are there with small modular reactors. Another area where the nuclear industry has been quite ahead is the use of centrifugal contactors for liquid-liquid extraction. So this is the primary method, at least liquid-liquid extraction, is to remove uranium plutonium using liquid-liquid methods that are used for extracting all sorts of other metals as well, outside of the nuclear industry. But the nuclear industry was ahead in terms of using centrifugal contactors. They're another classic, I'd say, example of process intensification, using a developed force, in this case, obviously centrifugal forces, to enhance mixing and also enhance separation all in one unit. And the sort of, square footage of area required for using these sorts of units in comparison to a traditional mixer settler is much lower area requirements, and when you've got compressed nuclear sites, that's a massive advantage. So again, there's still development issues, a lot of in terms of ensuring the mechanical stability of these centrifuges for extended periods of time. But these, generally, if you're intensifying a unit, you need to induce or introduce some sort of force, maybe mechanical force or other type of force, to increase the mixing while not increasing the size of your reactor. That's, so most intensifier reactors need a method to intensify. So in terms of nuclear effluent treatment, which we've done a lot of work on, really there are two primary processes. The focus is to remove the radioisotopes from the liquid, and people either use ion exchange or co-precipitation, and that happens in just about every nuclear operating plant for pond waters or other type of process waters. It's also used extensively in Fukushima to clean the cooling waters that are used to cool the molten cores. Both co-precipitation and ion exchange are used extensively, essentially, and we do work in both areas. And from that, you then need to process the solids. So, gravitational separation and flotation or ultrafiltration are generally used for solid liquid separation of co-precipitation waste. And we've sort of recently done a review where we've tried to establish different existing process intensification technologies from other areas, mostly from high value chemicals and pharmaceuticals, and how they may be suited to these sorts of effluent treatment operations. But I think this is one area where there's a lot of links to minerals processing as well, having to recover and recycle processed waters or reduce the volume of waste and tailings. A lot of these sorts of units may become useful for the minerals processing industry as well. So we separated them into sort of precipitators and reactor types, adsorbers and ion exchangers, and downstream waste separators. I'm going to talk examples of only about two here. So use of an agitated tubular reactor, which I'll go into at the end, and the use of air flotation for rapid solid liquid separation, which I'll talk to in the latter part of the talk. For the next 10 minutes, I'll just talk about our online characterization and just take one example from the acoustics work that we've done with the nuclear industry for over a decade. They've got a requirement to especially establish solids content, but also particle size remotely. So we've developed ultrasonic units that can be inserted in situ or put on the outside of pipes for remote measurement and characterization for their big transfer operations that are ongoing. And we tend to use sort of megahertz transducers. They both transmit and receive an ultrasonic pulse, and the echo basically the pulse scatters off particles in the suspension and you receive the echo, and by measuring changes to the backscatter strength and the level of attenuation, you can infer some particle properties. And as I said, the most common one we're focused on is concentration, but we're also doing some work on particle size as well. And the measurement principle comes from people in natural sediments. So people looking at sediments in estuaries and stuff, and they sort of have what I'd call a semi-empirical function generally that boils the backscatter voltage down to a bunch of parameters. Without us going into all of them, it includes concentration and particle size or particle radius specifically. So they're the two particle properties that we really want to know about. There's two acoustic properties that you have to develop calibration methods to measure: the scattering coefficient and the attenuation coefficient, and they are material properties. And you tend to do calibration measurements in well-mixed tanks, such as the one in the picture, to establish what these coefficients are for particular types of suspensions. And then you can then do your online monitoring and measure the concentration of size of particles in your transfer line or your sedimentation tank. So, for example, here's some concentration profiling using sort of more developed theory in the calibration tank. So you shouldn't get any changes in concentration, but you can at least use that to infer at what concentration the theory breaks down. At higher concentrations, you get a lot of interparticle scattering of the sound waves, and the established theory breaks down, but we can at least measure relatively accurately up into about sort of 70 to 80 grams per litre, which is very much in line with what's needed. In the nuclear industry, we're not dealing with sort of 20, 30, 40 weight percent suspensions in the nuclear industry, because they're very worried about the radiation, and most of the radiation is associated with the solids. And so there is an upper limit in terms of their forward processing of around 10% in terms of the solids concentration needed to at least have a reduced radiation risk. So I'll just briefly mention some of the larger scale work we've done in the nuclear industry, trying to establish one of their traditional horizontal clarifiers that they've inserted into one of these waste ponds. Basically, they've got a whole bunch of sludge on the bottom, and they vacuum the sludge up using a convoluted process I'm not going to describe, and then they deposit into a horizontal clarifier that is actually inserted into the edge of the pond. You can see it being a picture of it being inserted. And from there, it's supposed to consolidate into the bottom of the pond, and then it will be transferred to a solid encapsulation process that is running to basically put the waste into cement drums. And they had this operating, but they were getting relatively low levels of consolidation, and they weren't sure what was going on. So we were looking to use our acoustics to understand why. But we first established a sort of 1/3 pilot scale model to try to at least understand some of the fluid dynamics taking place in the clarifier. So this was still 9 meters cubed separator. It's just a big mixer settler basically, and so it's 1/3 the scale of the operational one, but it's still pretty big scale for us anyway. And yeah, the sludge just comes out, the inlet gets mixed and flocculated, and then it settles at the big settling zone, and then the outlet, the weir, takes hopefully the clean water to the other side of the tank. The tank was sort of split in half so we could recycle the water. And we had an array of both sampling ports and also our acoustic transducers, so that we could profile the solids concentration along the settling zone of the clarifier. This is just some of the results from the study. The first thing to note is that it was sort of running a sort of semi-batch mode. So this is what happens in the nuclear industry. It's not run continuously. It's run over a period of a number of hours. And what you see here is the sort of concentration as a color map. So from 0.1 being the highest in the clarifier to 0.7 being basically the bottom, and then sample position 1 being near the inlet and sample position 5 being at the outlet. This is results from the acoustics, and essentially yellow equals high concentration and blue equals low concentration. So you can see the buildup in particulates within the time frame because it starts with just water in the settling tank. But also you see a bigger buildup in the outlet. area. So it's more yellow towards the outlet and towards the weir. So this is opposite to what you'd want, obviously. You want everything to settle down in the inlet side so the weir is nice and clean. And it compared well to sampling data. The sampling data essentially showed the same trend and indicated why the operations were not being successful, because they were getting a build-up of particulates at the back end of the clarifier. And that was due to essentially a big recirculation current forming. So we did some CFD as well, but this is a well-known phenomena in water treatment. Any horizontal clarifier is going to have this recirculation current because you get a density current forming from the suspension that falls down initially and then gets brought back up towards the outlet weir. So in a way, this was used to prove the effectiveness of our acoustics, but it did just prove that the industry had got themselves into a tangle by using what they thought was a simple technique for sedimentation, but unfortunately, it wasn't very efficient because, well, lots of people know that horizontal separators require baffles, etc., to increase the efficiency. And because this was already installed, they weren't able to do much with this, but this prompted some of our investigations into using flotation as an alternative. We're also moving ahead with the acoustics. We're actually installing into the same operational plant, but in the mixing tank that is coupled with the cement mixer. And so we're having a single vertical array. And again, what they want to get out of it is solids concentration, primarily because that's where the radiation is. And they want a specific recipe, as it were, of about 10% solids going into the cement barrels, much higher, and they're at risk of having too high radiation, much lower, and they're just wasting money. At the moment, because they're getting low consolidation in the clarifier, they're actually just cementing water largely. And so what, may take a few thousand barrels, and these barrels are, hundreds of thousands of pounds per barrel, may take thousands more. So this is a massive impact on cost. Unfortunately, yeah, we've got this all ready to go. It's been sitting ready to be installed since COVID. And this is an idea of how long it takes in the nuclear industry. We've had this on the shelf for 4 years, actually, to be put in place, and our time frame for installation kits getting knocked back due to other operational issues, which are deemed to be more important. But anyway, that's largely a result from delays during COVID still. So I'm very hopeful this year. It was supposed to absolutely be last year, and then it still didn't happen. So maybe I can come back one day if we ever get that installed, and I can show you some site data. Anyway, I'll just briefly mention about the particle size aspect. So that was all, based on concentration, but of course the basic theory has a particle size, and it would be really good if you could measure simultaneously size and concentration from a single technique. We've been doing a lot of work using more advanced modeling approaches that are specifically designed for flocks, so they take into account the interparticle fluid. And as I said, most of these particles are flocculated, and trying to fit the model to experimental data to try to extract, both parameters simultaneously. We can't quite do that at the moment. What we end up with is sort of a family of curves. So I'm not going to really explain what these axes are too much on the figure, but Ka is the wave number times the particle radius. So that's our size parameter. And on the vertical axis is our attenuation coefficient that is modified to include the specific gravity of the flock. So we take into account density effects. And we essentially can fit the data to a number of mean sizes, and we get a different coefficient of variation if we do so, but we cannot say currently which mean size is correct. We essentially get the same order of fit in terms of the accuracy of fit by altering the coefficient of variation for different mean sizes. So at the moment, we don't know exactly what the sizes are unless we use an alternative technique, such as an FBRM or that in the size that they have here, the blaze. So we still need to do more work to be able to refine this to, be a specific mean size. And we're using sort of artificial intelligence to help improve our fitting. So is everyone else for everything, I assume. But, the goal is quite important. If we can get a single probe technique to give us both size and concentration, with no other input needed. That would be very useful for the nuclear industry, and very useful as an inline sizing technique for all sorts of reasons. But I mean, I think if AI can make Will Smith eat some spaghetti, it might be able to improve our understanding of these systems. That's the goal anyway. Okay, for the sort of latter half, I'll talk about the process intensification side of things, and mostly been focusing on effluent treatment. So as I said, co-precipitation and ion exchange are the two main methods. What's wrong with ion exchange? Why the need to intensify the operation at all? It all seems pretty simple. Just have some columns and away you go. And it's very much the go-to for industry if they can. It's much better system than precipitation operations. But it's actually operationally not very efficient. You have to use very low flow rates, or if you have pressure drop issues, absorption of heavy metals onto ion exchange systems is kinetically quite slow. So if you process your liquid through too quickly, you never end up exhausting your ion exchange properly, because you're kinetically limited by the exchange interaction. So you've got to basically dehydrate your ions and then exchange at the exchange sites, and that takes time. Also, you need to use large granular material, or else you have pressure drop issues, and that gives you a lower surface area to volume ratio. So in terms of material properties, ion exchange columns aren't very efficient. And so we've looked at it a couple of ways, one of which is using this agitator reactor, which I'll talk about at the end, and one of which is simply using flotation and looking at ion exchange from a simple batch perspective. So we use sort of the same type of materials that they use in Sellafield, which is clinoctillolite. It's a type of zeolite, and they have interstitial gaps and exchange sites to exchange with iron, such as sodium, that you can activate in the site pores. You can actually, if you run a really high resolution TM, actually see the size of these pores. So these are of the order of angstroms, around 1 nanometer, so these are sort of nanoporous, as you would say, or microporous. You get penetration to a few tens of layers with water, but these pores are very exchangeable. And you can also get absorption because the surface itself is normally quite negatively charged. But what we found is, as you probably would expect, as you increase the surface area, you increase your relative absorption capacity quite significantly. So if you go from large granular material to low surface area, and you just mill it, basically, you massively increase the relative performance of the material. But of course, that means you can't no longer run them in a column because the pressure drop would be too great. So our first goal was, well, if we use fine grained clinoctillolite, we'll get much better absorption, but then it's much more difficult to dewater, right? So very fine material, if you put it into a clarifier without flocculating it, then it would take forever to settle. So that's not an option either. So hence we've started looking at flotation as a way of expanding the amount, well, firstly, increasing the speed at which we can dewater, and also hopefully allowing us to dewater without the use of flocculants, which as another chemical species is difficult for the nuclear industry. I'll move forward from that. So, I mean, many people would have heard of flotation and used flotation for minerals extraction. And it's also been used a lot in the water treatment industry for many decades as a rapid dewatering technique. And I'm not sure anyone would ever use the term process intensification when it comes to flotation units, but really, again, they fit the bill. You're going from something that's really size intensive and time intensive, which is, horizontal clarifiers, as I've just talked about, to something that is much more space efficient and much more time rapid. So in a few minutes in a flotation cell, you can get the same type of separation efficiency as an hour or 2 hours in a horizontal clarifier. Of course, you have to do more. You need to be able to design the particle properties so they stick to bubbles, so partially hydrophobize them to an extent to allow extraction. And then also you need to worry about entrainment of liquid as well, as I'll go into. But nominally, we thought this would be a way of using much finer grade clinoctillolite, actually quite fine, sort of mean size about 10 to 20 microns. So high removal efficiency of radioisotopes, but then relatively rapid dewatering for onward treatment in cement. So the main type of isotopes we look to remove from pond waters is cesium and strontium. So most of our work here is with cesium at relatively low concentration, sort of 5 to 10 parts per million. That's the average sort of effluent concentration in these pond waters. And cesium is positively charged. You exchange it first with the material, but the clinotillite itself is very negatively charged. And so you have a very negative surface, even though you've got some cesium adsorbed, because it's exchanging with cationic sodium. It's only the surface adsorption that can change or alter the overall charge of the surface. So you still maintain a negative charge surface, and so therefore we looked at using a cationic surfactant to hydrophobize the clinotillite, because it's very hydrophilic itself. It's not going to float at all without a collector. We have used a few different cationic surfactants, but this one, CPC, worked the best. And so obviously what you have to do is get the concentration to a point where you've got a maximum, one layer of surfactant, and you don't over do the surfactant and end up with a bilayer forming. So we've done a lot of work looking at sort of adsorption isotherms, which we just plotted here in terms of the distribution coefficient on the left vertical, or surfactant absorbed amount on the right vertical. And really we're looking for where those peak. So where they peak is approximately where you have the monolayer to bilayer transition of the surfactant. And at that stage, you almost get 100% of the surfactant adsorbing. Why emphasize that? It means you need a frother as well, because it doesn't foam at that stage, because there's actually no free surfactant. It's all on the surface of the clino, because the clino is so negatively charged. So in this case, it's very efficient. You only need to add just enough surfactant to cause a monolayer formation to form, and you don't want the bilayer to form. So if you establish the concentration being of collector, then we can look at how using a frother changes characteristics, because there's no frothing of the system without frother, because as I said, all the surfactant ends up on the clino. So your clino recovery goes up as you add some MIBC frother up into a certain point. But you also get a slight reduction in the water reduction ratio. So we don't have two particle systems here. We're not trying to separate different particles, but we're trying to separate particles from water. So for us, the other key consideration is not just the clino recovery, but what our water reduction ratio is. So we can have systems of almost 100% clino recovery, but a water reduction ratio of 1 or less, which means all we're doing is just transferring foam from one container to another. So, but a water reduction ratio of 4 means that we're, removing, we're only extracting 25% of the water, while we're extracting 85% of the clino. This is through a one-pass system. We still would have to probably pass it through a second flotation system to increase that recovery slightly. But those water reduction ratios are much better than you get if you just settle this stuff in a clarifier, or at least on par with it. Again, you don't want to increase the solids content too much, because that increases the radiation. And so there's natural upper limits to how much you want to reduce the water. So this sort of system would still be pumpable, and that could be placed into cement, a local cement, factory for consolidation. Okay, so that works quite well. So we also were looking at using flotation to just remove a lot of the sludge waste that they have at Sellafield. So as I said, more as a direct replacement to that horizontal clarifier that doesn't work very well. And here we've been trying to design block copolymers that may act both as flotation aids and also as flocculation aids, depending on the situation needed. So there's a hydrophobic block. We've changed the block size to PNBA block, and then a hydrophilic polyacrylic acid block, and at neutral pH that deprotonates, and you end up with a negatively charged block. So these things, because they're block polymers, act as sort of macro polymer surfactants. So they micelize at a certain concentration, but below that concentration, you get interaction with the negative charge block and the mineral. And in this case, the mineral we're looking at is magnesium hydroxide, which is the main corrosion product of old cladding waste that are in these ponds. So in this case, they're actually slightly cationic, particles, because that's what magnesium hydroxide is. So the negative PAA block can interact with them, and hopefully the hydrophobic block will stick out, hydrophobizing the particles for flotation. But if you increase the concentration more, you actually micelize the system. And what happens in that case, you get a massive increase in the flocculation, because the whole micelles bind the particles really, really effectively. But in that case, you won't get any flotation, because it completely, the charge completely transfers to being negatively charged because of the micelles, obviously with the charge group facing outwards. So we looked at, flocculation with these polymers, and we've looked at different hydrophobic blocks. So the P25 has a smaller hydrophobic block. Sorry if you can't see that data very well. And the P200 has a larger hydrophobic block, and that shifts the critical micelle point to lower concentrations. So you get a big uptick in the settling rate once you go into the critical micelle zone, because it ends up collating the particles a lot better. And you can see maybe the bottom images, the actual microscope images of the flocks. You do get an enhanced flocculation post micelle point, but at that point you don't get any flotation. But if you float at lower concentration, so just below the critical micelle concentration, where again we assume we've got sort of maximum monolayer coverage of the polymer, you do get enhanced flotation, but you still actually get good flocculation as well. So we look at the collection efficiency factor, which is another way of looking at the level of particulate removal versus liquid entrainment. So if it's below 1, that means you're just removing liquid, you're not even removing the particles. But anything above 1 means you're removing more particles than liquid, which is obviously the goal. And we can get, efficiency factors similar to sort of what we had in the other study of 3 to 4, which is beyond even using molecular surfactants, as long as, I said, we're below this critical micelle point. But we still get actually quite rapid flocculation. So there's a little image there with a big sort of bed of large flocks, which I have to say wasn't necessarily intended, but essentially we were floating the finer section, finer fraction of the particles, and we were still getting enhanced flocculation to a point which they were settling so rapidly. We feel application in a combined flotation separation cell would be really useful. So the heavies simply just come out like they would from a vertical clarifier, a vertical thickener, and then you float off the finer segments out of the top. And that's also, some degree of aggregation is obviously advantageous for flotation as well. These are very fine structures, and so some degree of aggregation is still required for floating these particles as well. So I'll finish now by talking about this thing that I've mentioned before, looking at the agitated tubular reactor. This is a type of intensified reactor, and as I said, all type of intensified reactors have some force, normally mechanical, or it couldn't be rotational force, to intensify what would normally be a plug flow system. So this basically has an inner agitator within a tube, and you just shake the agitator and tube side to side. It's got a series of reactor tubes that you can run in parallel or series. So basically you get counter motion between the agitator and the outer tube, and that generates local shear and local velocity forces that help agitate and keep particles suspended. And it's all radial, side to side, rather than streamwise, up and down. And so actually you have, in terms of the overall fluid motion, you can pump it at quite low levels, so you can change your overall residence time independently to the level of shear in the system. So you can change the shaking motion in terms of the hertz you put in, and you can independently change the residence time of the reactor. And this has generally been used for organic reactions, certainly solids catalyzed reactions, where the solid catalyst maintains suspension. And we've looked at a number of ways of using this as an intensified reactor. And I'll just talk about the ion exchange one. But I'll firstly mention, we've done a lot of characterization of this reactor, where we've used ultrasonic profiling, image analysis, and CFD models to establish the overall mechanism by which the agitator works. But basically, you see this horizontal velocity go up and down. And so that's a local shear velocity, right? So the overall tube is moving, so the overall velocity is not moving at all, but the differential movement of the agitator causes rapid increase and decrease in horizontal velocity that leads to the shear that's needed to mix. And so it's going, in this case, plus minus 100 millimeters a second over very short timescales. And it's that relative motion that causes the shear in the mixing. And we've established a CFD model that works very well at predicting the mechanical relationship measured experimentally. There's a little bit of a difference due to bumping in the experimental system, but now we can look at the turbulent kinetic energy and the turbulent dissipation rate of using the simulation that we've developed from our mechanical understanding. So we've looked at using it as a precipitator, and I think in the interest of time, I'll just skip through this, other than to say it's a very useful way of increasing the consistency of a composite precipitate used to increase sedimentation rates and filtration of various wastes. In this case, this was removing dyes from liquid effluent. But I'll talk about it using it as a replacement for a static ion exchange column. So here you've got a model of a static ion exchange column. You simply drip the water through, which contains your radioactivity. It's nice and yellow there. And you measure the outlet concentration or the equilibrium concentration. And for nuclear applications, you want that pretty much to be zero. And you do that for over and over again until you reach breakthrough and your concentration at the outlet rapidly approaches that of the inlet. And that's how you would establish how long you would normally operationally run your ion exchange columns in any type of industry. So what we basically did is fill the agitator bar with ion exchange resin and use mesh to make sure it didn't move anywhere. And so our understanding was it sort of operates a similar way. You can change your overall transfer time or residence time, but the increased mixing should enable better contact between the liquid and the ion exchange and better resolution and kinetics between the solutes and the ion exchange themselves. So we were hoping this agitation increase the efficiency of our ion exchange column over a static vessel. So what you tend to do, you measure these breakthroughs. So you measure the number of column volumes that you can extract until your outlet concentration rapidly goes towards your inlet concentration, showed on the vertical axis there. And then you fit that to a model to extract out the material properties that you want, which is the overall equilibrium absorption amount within the column. And that's some static results versus the column results. In this case, it may not make much difference what it looks like. It's just a bunch of curves, but essentially you can boil this down and work out the overall number of columns you need to process before saturation of the column and the overall final equilibrium absorption amount of the grains within the column. And what you get is the number of column volumes to break through, in particular, increases in the ATR by about 30%. So we were going for a particular low flow rate of around 125 column volumes up into around 175. So that's a 30% increase in the number of columns you can process until reaching the same level of exhaustion or the same breakthrough level. And that means you replace your columns 30% less, and so that's going to save you money, but also save you waste volume. The nuclear industry are dealing with thousands of meters of cubed of ion exchange resin that have accumulated over decades, and so this gives a real potential to reduce the burden of exhausted waste by increasing the local efficiency. But we also can process it at much higher flow rates, so we actually got smaller residence times and also increased performance. So there was a little bit of a difference in terms of the volume of the vessel, but we're essentially being able to process 3 to 6 times faster for actually 30% higher performance. So we need less columns and they work better than through the static ion exchange resin. And what we're hoping to do is turn the columns into pellets and basically charge the column up like you sort of would with a reactor fuel. So you have charged pellets of ion exchange that can be easily replaced. So anyway, I just got one thing to say, actually, completely separate. But something else that we're doing at Leeds is we're just opening what we call the multiform facility, which is our multi-phase flow and characterization facility. That's just been commissioned now, so I don't have any pictures, but it's a £3 million facility funded by government to look at multi-phase flows, as the name suggests, bubbles, particles, and liquid. Focus on nuclear, but also looking for knowledge transfer opportunities in other sectors such as minerals. We have sort of state-of-the-art multi-phase flow loop with all sorts of angles and bubble inlets, and basically giving the flexibility to run any sort of multi-phase flow you can think of, and a variety of instruments that are used to characterize the flows, both in terms of the turbulent kinetic energies, so particle image symmetry and laser Doppler anemometry, and also inline FBRM to measure the particulate properties as well. So yeah, putting it out there, this will be operational soon. We'd be very happy to have some people over to do some work in it for collaborative purposes. It's funded initially sort of by the university for the next 2 years, so costs are remaining low while we're in a commissioning and development phase. So if anyone wants to do any multi-phase flow characterization, please get in touch. And on that, I also have a postdoc position opening to help us on this platform too, which should be online in the next few weeks. So if anyone wants to join in sunny Leeds, then please get in touch with me. It's definitely sunny for a month at least of the year. Yeah, so I'll skip the summary and just say thanks for listening.
Hi, Tim. Thanks for providing this seminar today. It's very interesting, and certainly, and I'm sure George has probably conveyed this already, that there's lots of scope for some of the things we're doing that would be, I think, relevant to BNFL. But I imagine that you need to concoct model systems to work with. So have you got sort of model systems that if one was to get involved in this sort of space that we could use?
Yes, we do. I mean, it depends on the wastes. Most of the corroded magnesium waste, they have basically different grades of model systems, they call it. So the waste came from aluminium and magnesium cladding, and most of the worst sludge is from magnesium-based cladding because it reacts with water very rapidly. So they do non-radioactive sort of digestions of actual cladding, spare cladding that hasn't been through a reactor, and that's their A grade, and that costs a lot for them. We have done some studies comparing different grades of materials, but a lot of our work, simply comes from just fine magnesium hydroxide powder. But for most intents and purposes, commercial magnesium hydroxide powder, in terms of particle properties, works fine. We've also looked at sort of actual pond sludges that have a high organic content from dairy farms. So they do try various things to compare to their radioactive samples. But yeah, I mean, fine magnesium hydroxide powder would be a pretty good go-to, I think, for a lot of their waste problems.
Right.
Thank you. Yeah, and I think a lot of what you said about process intensification echoes what Kevin's been saying about the current rate of increase of the size of flotation cells means that in 10 years will be as big as an Olympic swimming pool.
Yeah.
And we need units like reflex flotation cells, which will be, instead of an Olympic swimming pool, will be a couple of meters in diameter.
Yeah, precisely. I mean, I briefly went and spoke to Prof. Jamison Newcastle last week when I was there, and he mentioned about the burgeoning size of flotation units, and I'm like, yeah, from a process intensification perspective, that's exactly what you don't want. Yeah, exactly.
Fantastic. Okay, well, let's thank Tim again.
Great, thank you. Thank you very much. Thank you very much
for coming in person, and we'll have the rest of our afternoon to have some more chats. Okay, thanks everyone.
Thank you all for joining online.
Yep. Catch you next time.